In this video, we talk about modules and packages. In Python, modules and packages help make coding easier, especially for big projects. To put this into context, functions are like a small tasks that you can use over and over, so you don't have to write the same thing many times. Modules are files that hold a bunch of related functions together, making your code neat and easy to find stuff. On the other hand, packages are bigger collections of modules, organizing everything into a system that's simple to use and understand. All these parts work together to make Python coding smoother, letting you build complex programs without getting lost in the details. To get us started, let's revisit functions. Functions in Python are blocks of reusable code that perform a specific task. And we use the def or def keyword followed by the function name, parameters, and a block of code that usually returns some values. Let's revisit one of the examples that we had before. In this case, we want to define a function which is called isPrime. And this function accepts a number, a positive integer. And the goal is to figure out whether this number is prime or not. Just to remember the definition of a prime number is a number that exactly has two distinct positive divisors, one and itself. And the goal here is to return a Boolean value, true or false, which indicates whether the number is prime or not. This is kind of a simple problem because what we really need to do, find or list all numbers from 2 up to this number that we want to check whether it's prime or not, and then divide this number by the numbers that we have in this list and look at the remainder after the division, right? So if the remainder after division is 0, this means that we violate the definition of a prime number, and therefore we have to return false. And if we go through all these numbers in this list, which is called found primes, and we don't get any factor with the remainder being 0, this means that this is indeed a prime number. And in order to kind of go a little bit more into details here, you can see that we start from 2 up to a square root of the given number that we have here. So if you want, you can iterate or go through all the numbers up to this number that is given here. But in general, we can show that it's enough or sufficient to put the maximum to be a square root of this number that we have here. That's why we have this raised to the power of 0.5. But this shouldn't change the result, and it's more efficient to use the smaller range or list here. And after that, we use a for loop to iterate over all these elements in these found primes. And if the remainder of the division of num by factor is equal to 0, then we have to immediately return false, because then we know that this is not a prime number. And otherwise, if we go through all these elements in found primes and we do not return anything, meaning that this statement is false, then we return true at the end of this function. So just to see how this works, so let me run this cell. We can try a few options here. So you can see that if we provide 3, 3 is indeed a prime number, so we do get true. Then for 4, 4 is not a prime number, because if we divide this by 2, we get 0, the remainder after division. So that's why you can see that we correctly see that the result is false. The same thing with 9, because 9 is actually 3 raised to the power of 2, so we get false. And for 11, this is really a prime number, so you can see that we get true, right? So for 11, we can only divide these by 1 and itself, which is 11. And we do not have anything in between that we can divide this number with, and we get 0 for the remainder of the division. So the nice thing about this function right now here, this df is prime, is that now if we have a bunch of numbers that we want to see whether each one is prime or not, we do not have to repeat this process every single time, right? So that's the part that we say the code is modular, because we have written one function that is modular in a sense that we can provide a given number and it will return the result. So this means that now we can take this to the next step, right? So what if I want to give a list of prime numbers up to some maximum number, right? So let's say you're interested in finding the list of all prime numbers up to 20, right? So we know that 2 is a prime number, 3, 5, and then 7, etc. But the question here is, how can we find all of these up to some maximum? And this is kind of like, given the function that we have before is prime is very easy to implement because we can start an empty list and then we can iterate over all numbers in the range 2 to this num max. And the way that we define here is that we do not necessarily want to include num max, so it's exclusive. If we want to make it inclusive, we can just add 1 here. But this is the way that we define this function. That's why the doc string is very important, because you can really state all the assumptions and requirements that you have. And the way that we have written this, this num max is exclusive. So we do not need to be worried about adding 1 here. And so now for each number in this list, we're going to call that function is prime. And if it is true, meaning that if that number is actually a prime number, then we're going to use the append method to add that number to this empty list that we have. And at the end, we're going to return the result. So let's run this cell. And now if let's say I use list primes 20, so this means that we're going to see whether 2 is a prime number, 3, 4, 5, all the numbers up to 19 inclusive. And you can see here we correctly get the result like 2, 3, 5, 7, 11, 13, 17, 19. But the cool thing here is that you can increase this basically like let's say 200 or any number you want, right? So now you have the list of all the prime numbers up to 100. So this is something very helpful. So let's put this back to 20. So here is what we want to do next. So right now we have 2 functions. One is prime, which checks whether a number is prime or not. And the other one is list primes, which lists all the prime numbers up to some num max. So what I want to do, I want to start by restarting the kernel. So you can see that here we can go kernel, restart, and clear output. And the reason we do this is because we want to make sure that we have a fresh notebook. So we do not, right now after restarting this kernel, we do not have these functions defined, right? So I can, for example, insert a cell, or let's just run this, right? So if I just run this, you can see that now it says that this list primes is not defined. And that's something we expect because I just restarted the kernel. So if you want to have this like function defined, you need to run these previous cells that we have here. But here what we want to do instead, I'm going to copy this function that we have here. So I use Command C or Control C. And then I'm going to create a new Jupyter notebook. And I'm going to paste that function, the definition of that function here, right? And also the other thing I want to do here is going back to this previous notebook and copy this other function that we have. So one is prime, the other one is list prime. So the other thing also we want to do, I want to change the name of this notebook from untitled to primes. So this means that we have now a notebook or file that is called primes, which includes some functions related to prime numbers. And what you can do right now is actually you can download this as a Python file. So if you look at it, here there is this option python.py. So this means that if you use this option, you're gonna save something called primes.py, right? So uh, what we really want to do right now is to create this Python file, which is primes.py, which includes these functions. And so why is this important? This is very important because now if we have multiple notebooks, I can just import this primes.py and I have access to all the functions that I have here. In this case, this may not be a big problem because we only have two functions and you can always copy paste them. But this is not a good idea because if you change one of these functions in one notebook, then you need to make sure that you apply those changes to all other notebooks. Whereas in this case, you have one primes.py that contains these functions. And if you want to make any changes, you can do it here. And once you import these to other notebooks, you're going to be able to use the most recent version. And so that's the idea that we have here about modules, right? So a module is a file like primes.py that contains Python code. It can contain variables, functions, classes, everything that we have seen so far in this class. And this allows us to organize code into separate files for better maintainability. And the nice thing is that modules can be reused across different parts of a project or even multiple projects. And in this case, we created this module, which is named primes.py. And when the interpreter executes this line, right? So again, let me one more time restart and clear output here. What it does, it searches for that Python file that we created. So once you created that primes.py or downloaded that file, make sure that it's in the same folder or directory that you have your notebook. And in that case, if you run this, you can see that now we can import these primes. But something that is very important, like say I make a mistake and I put double two S's here. And you can see that in this case, if I run this, I get this problem or message that it says that no module name primes with two S's. So remember, if you get this error message, this means that the interpreter cannot find primes.py. So you need to make sure that you have that Python file in the same folder or directory. And if you do, you should be able to run this cell. The other thing that is important is that this primes file contains those two functions we have, isPrime and listPrime. But if you want to just use them as is, like for example here, say print isPrime4, you can see that again, you get an error message that says isPrime is not defined. And this is because the module contents are only accessible when prefixed with the name of the module via dot notation. So this means that if you think about this as a hierarchy, you have this module, which is called primes, then use the dot notation dot, and then the name of the function. And if I run this, you can see that now we get the correct answer, right? 4 is not a prime number. So that's obviously one way of importing modules, just say import the name of the module. But as you can see, this can be somewhat inefficient because you have to always also use the name of the module and then the dot notation. So if you want to avoid this extra step, you can use this syntax, which is from the module name, here is primes, import names that you want. So in this case, let's say you just want to work with isPrime, and so you can say that from primes, import isPrime. And if I run this, you can see that now I do not need to use the dot notation anymore, right? Because we specifically say that from this module, import these names, or for example, here, these functions. In some cases, you may have multiple names and you don't want to list all these names here. So Python actually has a nice way to get around this problem, and that's using this notation. So if you say from the module name import star, this means that you want to import all these functions or names that we have in this module. So in this case, you can see that we are checking whether 4 is a prime number or not, and list all prime numbers up to 10, right? And so we get 2, 3, 5, and 7. So these are very, important things to know about like how to import modules and how to use what's included inside these modules. So once you understand this syntax and this structure, then you can see that some of these modules that we have seen even before in this course are now they really make much more sense, right? So for example, we have something called time module in Python, which provides time-related functions. So allow you to work with time values, perform operations such as measuring time intervals, pausing the execution of a program. So anything that really relates to, to time when you want to run Python programs. So the very first thing, if you want to use the time module, is to import this, right? So this means that somebody has written this, time.py, which includes a lot of functions, classes, etc., right? And remember, you can always use this type function in Python at any point to figure out what the type of this object is. And you can see that here it says it's a module, right? So now we know exactly what a module is because we created one. So inside this module, somebody has written this function, which is called process underscore time or process time, which is used for measuring the CPU time consumed by a specified process, right? So something that is very important is efficiency of your code, meaning that how long does it take for your code to run and get you the result that you expect. And the way that you can use this process time is that before the execution of the block of code or piece of code that you want to see how long it takes, you're going to call this function and assign the value to a variable, let's say called T0. This is obviously optional. You can use any name you want. And after the execution, you again call this function and you save the result in another variable, which I call it T1, right? So these are the kind of like a start, a stop that you use for timing, right? So in this case, you subtract T1, T0 from T1. So now you have T1 minus T0. And this represents the elapsed time or the execution time and serves as a metric to gauge the efficiency of your program. So in this case, you can see that, I have this start process time and end process time. So this is right before and after this for loop. So inside this for loop, I'm going to have this range of numbers up to 10 raised to the power of 7, right? So that's like 10 million, and I'm scoring each element in this range. Obviously, this is not really doing anything helpful right now, but that's the goal here, to just have something that we know is going to take some time because we have to go through 10 million elements. And before then, we use this time.process time to have the start point or start time. And right after, we use that to have the end time. And obviously, then we have to subtract these two times to find the elapsed time. And I'm using the formatted string or f string to print the result. So as you can see, this takes, some time, and you can see that it's about 1.5 seconds, right? Because you have to go through these 10 million times. So depending on, on the CPU that you're using, you may get different results. It may take longer or it might be faster, but that's something that I get right now running here. And possibly if I run this multiple times, I should be able to see different results. So you can see that now, I see some differences in the second decimal points. And just to recap, what we're using here, this 0.3f, that tells us that you want to have 3 decimal points, right? So if you want really like just look at the first decimal point, you just use that as 1 here. So you can see that now we have 1 decimal point. But if you want, you can use, for example, like 5, right? So now we will have 5 decimal points. So that really depends on the precision that you're looking for. So I'm going to put that back to 3. Okay, so now let's go to the very familiar example, the math module. We've been using this from lecture 1 in this class, which provides a set of mathematical functions, right? And these functions cover a wide range of operations, basic arithmetic, trig, logarithmics, exponentiation, and more, right? So similar to the time module, you have to first import this. And this means that there is something called math.py. And you can look at the type of this to make sure that this is indeed a module. And now, because in this case, we just imported this math module, you can see that we have to use the dot notation, the name of the module, dot, and then the function that you want to use, right? So that's why we have to use this dot here, because this tells us that this skrt is part of this math module, and we have to show this hierarchy here. And here we're looking at the square root of 25, sine of 30 degrees, which we first, convert this to radians, because that's how the math.sine expects to get inputs as radians. We look at the factorial, which we, at some point we wrote this function, but obviously this is implemented there. So you get the result that we have. But just to kind of clarify these, let's say for the skrt function, if you don't want to use this notation, we can say from math import skrt, and now you can just say skrt25, and we find these results. So in this case, we do not need to use this dot notation anymore because we directly imported skrt from math. So this really depends on you, which like syntax or notation is more convenient depending on the complexity of your projects. The other module that we want to cover here, which is kind of like very important, is this OS module. So this allows you to interact with your operating system, for example, figuring out the current directory you are in, and environment variables and more. So for example, one of the functions that we have here inside this operating system module is get CWD, which stands for get current work directory. And so you can see that in this case, if I run this is basically the place that I have included this right now, this notebook. So this is very helpful because sometimes you may have multiple directories or folders that you have your files and notebooks. And so you want to make sure that you are in the right place, and you do not really need to use traditional ways of checking these to go through different folders. You can just use this os.get current work directory and get this information. So let's revisit something else that we have used before, like the Numpy random module, right? We are familiar with this when we talk about Numpy data structures. So remember, within Numpy, we have a module called random. So that's how, again, we show the hierarchy that random is part of Numpy. And this has a lot of functions and classes for generating random numbers, right? For example, using different distributions, uniform, normal, or Gaussian, and also like, random seeding, permutation, etc. So in this case, if you want to use this random module, you have to first import that. And remember, in this case, we have to, again, use the dot notation to explain that random is part of the Numpy. So then we know where to find this module. And we use the type to show that, yeah, this is actually a module. And once we import this, now you can see that we can access to the functionalities that included inside this random module. Like one of them, for example, is this rand n, right? So again, this is the random module, and you have to use dot rand n to show that rand n is part of the random module. In this case, we will generate 5 random numbers according to the standard normal distribution. And this really takes us to the next topic, which is a package. So what is a package? A package is a way of organizing related modules into a single directory hierarchy, right? So think about, for example, NumPy. In this case, you have a random module, you have a module for performing linear algebra operations. And obviously, you can use this as separate modules, but it is really nice if we can put these all together. So now we have another level or another um, like way of organizing these together, and we call this a package. And also this is something that sometimes is known as a library, so that's why we called before a NumPy library, but indeed it's a package, right, which contains these modules inside it. And in order to import modules within packages, you can either use the dot notation that we did before, or if you don't want to use the dot notation, you can use this from package name import module name. So you can see here from NumPy import random, and so this means that now random is defined, and you can say random.randn. But just to clarify, if you don't want to use this from NumPy import random, you can just say NumPy dot random dot randn. So really depends on, the way that you feel more comfortable with defining these sort of like, methods or functions that we have here. Something else that you have seen before too is that we can use an alias, right? So for example, you can say from NumPy import random, but for the other reason, you don't want to use the name random. You want to use something like, let's say, shorter. And you say that now import this as actually RDM. So this means that you give a new name to random, which is RDM. So from now on, Python understands that RDM refers to random, and random is part of NumPy. And if you run this, you can see that we get the correct result or what we expected. And the other thing also you can do is that, you can say that like from numpy.random, because this shows the hierarchy, right? It shows that random is part of numpy. We want to import randn. So in this case, it gets much easier later on because you don't need all the dot notation, right? So you use that once here, you imported this randn, and from now on, Python understands what randn is. So in this case, again, we get 5 randomly generated numbers from the standard normal distribution. But now this gives us also really good opportunity to talk about scikit-learn, right? Because this course, the goal is to talk about machine learning and data science. And the most widely used library or package is scikit-learn, which the actual name in Python when you want to import it is actually sklearn. So that's something to remember, even though it's officially called scikit-learn. The name is sklearn when you want to like import it, right? That's the name that we use. So scikit-learn, again, is a machine learning library that provides tools for data analysis and modeling. It's built on other libraries and packages such as NumPy, SciPy, Matplotlib, which is for visualization. That's the topic of our next video. And so therefore, it provides a very user-friendly and efficient platform. And scikit-learn offers a wide range of machine learning algorithms for classification, regression, clustering. So we're gonna actually go through, these algorithms and the way that we can use scikit-learn for the rest of this class. So that's something that we're gonna go through these things that we're gonna talk about them. But in this video, we want to just kind of like talk about it from the module and package perspective to be able to understand how this hierarchy here works. So as we said, this library or package include modules, right? And these modules are for different purposes, such as data pre-processing, model evaluation, model selection, etc. And so one of the things that, for example, very popular and you need to use when you're working with machine learning and data science problems is this linear module. So inside linear module, you have multiple classes and algorithms that you can use to perform or use linear models for both regression and classification problems. And so the way that this works, in this case, we import NumPy as NP. So that's importing the NumPy library, and we use alias to just call it NP. And so remember, sklearn or scikit-learn is the library or package that we have. So that's like the kind of like the big umbrella that we have. And then inside that, we have a module called linear model, right? So which includes functions and classes that can be used for running linear models. And one of them is this linear regression. And this is something that you already defined a class to replicate some of the functionalities of linear regression. But if you go to the documentation page here, you can see that in this case, linear regression is a class, like very similar to the class that you defined in one of the previous homeworks, that can be used for performing ordinary least squares, right? So in this case, you can see what are the input parameters that you can have here, some of the attributes, etc. So you can see now the way that this relates to actually object-oriented programming we had in previous lectures. But in this case, you want to very briefly just talk about more like from the functionality perspective. So let's say you have a very simple problem where you have this independent variable x, which contains 1, 2, and 3. And then you have the dependent variable y, which is 2, 4, 6. So in this case, it is obvious that the dependent variable y is simply 2 times the independent variable, right? Because when we provide 1, we get 2. When we provide 2, we get 4, 3, 6, right? So we obviously have y equals 2 times x. And this is called linear regression because this is basically, the way that we look at this is we want to find the equation of a line that connects these two variables, y equals mx plus b or ax plus b, right? Where a or m is the slope, and then the b at the end is like the intercept or y-intercept. So in this case, since we are importing linear regression, the only thing we really need to do is to instantiate this class and create an object. And obviously, we have multiple options when we want to do this. And one of the options is that we can set the fit intercept to be false, because remember, in this case, we know that we don't have an intercept. Y is simply 2 times x. And we just want to find that coefficient or a slope 2 and see if that works. So once you instantiate this class and create this object, now you can use .fit. And what this does, very similar to the class that you defined before, in this case, you're going to find or estimate the slope that we have here that connects y and x, right? So that's kind of like what we call the training in machine learning. And once you find the slope, now if you have a new independent variable, which is 4 here, now we can multiply this slope by this independent variable and find the value of the dependent variable, which is here our prediction. But the nice thing is that this model object that we have here, once we do the training, also has some attributes that we can use to find more information about this model. So in this case, what we are really doing, we want to find what this coefficients or coefficient here is, right? So as we expected, the coefficient is 2. And since this is a very simple problem, we don't have any noise or any errors here in the data, we can simply find that, well, yeah, the coefficients is 2. And as we said, now if you want to predict the dependent variable for 4, we're going to just multiply 4 by this value that we found here, the slope or coefficient, which is 2, and we multiply them and we get 8. Okay, so in this video, we talk about, functions, classes, modules, and packages. So it's kind of important to remember the hierarchy here, right? So we have these smaller pieces that we can combine together and create modules like that primes.py or like numpy.random. And then you can put all of these modules together to find packages or develop packages like Numpy or sklearn, or we're going to talk about matplotlib for visualization. So that's like the hierarchy there. In this notebook, we have 3 homework problems. Just to make sure that I didn't miss that, yes, we do have 3 homework problems. In the first problem, you want to create a Python file, which is actually a module called math operations. And this is supposed to have 3 functions inside it. So these are the functions that you can add numbers, multiply, take a number and return its a square. So these are simple functions, but I just want to make sure that we understand how to create these modules. And once you create this module, you're going to import it, right? And then you're going to be able to, for different numbers, you can perform these 3 operations. So that's what this homework problem 1 is, to create this Python file, put it in the same directory and importing it and making sure that your code works as expected. The second problem is you want to use one of the features in sklearn. So sklearn has actually a module called pre-processing. So this is for pre-processing your data. And we have seen an example of this, which was actually, this min-max scaler, where you provided a 1D array of numbers, and you want to scale these numbers to make sure that they're always between 0 and 1. So meaning that regardless of what the input values are or the given values are, you want to make sure that the pre-processed values are between 0 and 1. And so we did this from scratch previously, but now you want to use this pre-processing module. So remember, sklearn is the package or library. Inside that, you can access to pre-processing. So it's sklearn.preprocessing. And inside that, we have this min-max scaler class where you can create objects. And in this case, you want to provide this 1D NumPy array to this min-max scaler and be able to transform the data and print the result that we have. For sort of like reference here, I have included the link for this min-max scaler. So similar to what we saw with linear regression. So for each class that we have here, we have very well documented web pages that you can go through all the functionalities, what expected in terms of inputs, what you're expected to get from these classes or objects. So that's something that I want you to kind of practice and learn the way that you can read these documentation pages and be able to use them. This is very important because as you start your journey in machine learning and data science, you need to be able to understand these documentations to be able to use them. And the last problem is more or less just writing a function. So in this case, you don't really need to develop a module or package, but it's a good practice because we're going to need this later on. And that's about finding outliers in your data. So one way to finding outliers is known as the interquartile range or IQR method. So in this case, we are using NumPy and it's provided functionality to find outliers. The idea is very simple. So once you have a set of numbers, you're gonna find the first quartile or Q1 and the third quartile. So this is, obviously something that you can use NumPy's built-in functions and classes to find these, but just to give you an idea, like the first quartile is the 25th percentile. So this means that a number where 25% of the data lies below that number, right? So that tells you kind of like about the distribution of your data. And the third quartile, or Q3, is the 75th percentile, which means that 75% of your data falls below that number. And in order to find these numbers, you can use NumPy's, functions and classes. And once you find this Q1 and Q3, then you subtract them. So this shows you the middle 50% of your data, right? Because the first one is the 25%, the other one Q3 is 75%. So what you have in the middle is the 50% of your data. And this really tells you the data set's spread. And in order to find outliers, you're looking for those points that fall below Q1 minus 1.5 times IQR, and that's that interquantile range, or above Q3 plus 1.5 IQR. So this allows you to find extreme values and label them as outliers. So in this case, you're going to work with these cell that is provided here to be able to find these outliers in this array of 100 numbers that are generated using a normal distribution.